Let me tell you something that should keep you up tonight. Right now, as you listen to this, a chunk of ice older than our sun is sailing away from us. Came from another star. A dead star, most likely. A star that burned out before the Earth was even a thought in the cosmic mind. An ancient stellar furnace that forged planets, moons, and comets around itself when the Milky Way was young, when the galaxy was still assembling itself from clouds of hydrogen and helium, when the heavy elements we take for granted, carbon, oxygen, iron, silicon, were still being manufactured by the first generations of massive stars. And when we pointed the most powerful telescope ever built at this thing, the James Webb Space Telescope, a $10 billion instrument sitting at the second Lagrange point, 1,000,000 miles from Earth, folded like origami and launched on a prayer and a rocket, we found something inside it that made planetary scientists sit up in their chairs. Something that made astrophysicists stare at the data reduction screens and say, out loud, that can't be right. Deuterium, not just a little, not just a trace amount within the margin of measurement uncertainty. An amount 10 times higher than anything ever measured in any comet. Ever. In the entire history of cometary science. An isotopic ratio so extreme that it sits 12 standard deviations above the mean value measured in every protostar in the galaxy. 12 sigma. Let me put that in context for you. In experimental physics, we celebrate at 5 sigma. That's the threshold for declaring a discovery. 5 sigma means there's a 1 in 3.5 million chance that the result is a statistical fluke. When they found the Higgs boson at CERN, that was 5 sigma, and they popped champagne and gave out a Nobel Prize. 12 sigma means the probability of this being a coincidence is so small that the number of zeros after the decimal point would fill this entire script. It means the deuterium enrichment in 3I/Atlas is not a fluctuation. It's not measurement error. It's not a calibration artifact. It is a signal from an environment that no longer exists anywhere in our observable neighborhood. So what is deuterium? It's heavy hydrogen. Regular hydrogen, the most abundant element in the universe, has 1 proton in its nucleus and nothing else. Deuterium is hydrogen with a bonus. 1 proton plus 1 neutron. It's heavier. It behaves differently in chemical reactions, especially at low temperatures, because that extra mass changes the zero-point energy of any bond it forms. And here's the thing that connects deuterium to the title of this story, the thing that connects a frozen comet from the dawn of the galaxy to the most ambitious energy project in human history. Deuterium is the primary fuel for nuclear fusion. When you fuse deuterium with tritium, another hydrogen isotope, this one with 2 neutrons, you get helium-4, a free neutron, and 17.6 million electron volts of energy. That's the reaction powering tokamak designs at ITER in southern France. That's the reaction powering the National Ignition Facility's laser experiments. That's the reaction that, if we can ever bottle it, would give humanity effectively unlimited clean energy for millions of years. It's also the reaction that powers the sun. Every second, deep in the solar core, where the temperature hits 15 million degrees and the pressure is 250 billion atmospheres, hydrogen nuclei are being squeezed together so hard that the strong nuclear force overcomes their electromagnetic repulsion. Protons fuse with protons, creating deuterium as an intermediate step, and deuterium fuses with more protons, building up to helium. That chain reaction, the proton-proton chain, releases the energy that illuminates our entire solar system. The energy that makes life on Earth possible. The energy you're consuming right now because the photons that grew the food that became your breakfast started as gamma rays in the sun's core about 170,000 years ago. Deuterium is the key to stars. It's the key to fusion. It's the key to the universe's energy economy. And this rock from another star system, this ancient, frozen, battered traveler that has been drifting through the void for longer than the sun has existed, just sailed through our solar neighborhood carrying a concentration of that isotope unlike anything in our cosmic backyard. A concentration that reflects conditions in the early Milky Way. Conditions that no longer exist. Conditions the modern universe has essentially erased. That's what I mean by fuel the universe forbids. Not that deuterium can't exist, obviously it does. The universe made plenty of it during Big Bang nucleosynthesis, in the first 3 minutes after the cosmos began. But over time, stars consume deuterium. They burn through it almost immediately when they ignite. Every generation of stars that lives and dies reduces the total deuterium budget in the interstellar medium. What's left gets recycled, mixed, heated, enriched with heavier elements. The ultra-cold, pristine, metal-poor conditions that could concentrate deuterium to the levels found in 3I/Atlas. Those conditions belong to the Milky Way's childhood. They're gone. 3I/Atlas is carrying a chemical fingerprint that the modern universe has erased everywhere we can see. Now, let's be absolutely clear about what this means, and what it doesn't. This does not mean aliens sent us a fuel pod. It does not mean 3I/Atlas is a spacecraft. It does not mean some ancient civilization stockpiled fusion reactant in a comet and launched it across the galaxy. The Breakthrough Listen initiative, the most comprehensive SETI program ever conducted, already pointed the Green Bank telescope at 3I/Atlas. That's the largest steerable radio dish on the planet, 100 meters of collecting area parked in a radio-quiet zone in the mountains of West Virginia. They scanned every frequency from 1 to 12 gigahertz using 4 different receivers with sensitivity down to 1/10 of a watt. That's less power than the LED on your phone charger. They found nothing artificial. No signals. No technology. No modulation. Just the quiet electromagnetic signature of a natural object doing what comets do. The Meerkat array in South Africa scanned it separately across 900 to 1600 megahertz. Nothing. The Allen Telescope array observed it. Nothing. The Murraying Radio Telescope at Parkes in Australia hit it 3 separate times, July, September, October, with an ultra-wideband receiver sensitive from 700 to 4000 megahertz. Nothing. 3I/Atlas is not a spacecraft. It's a comet. But it is the strangest comet we have ever seen. And the deuterium is just the tip of the iceberg, or perhaps, more accurately, the tip of the ice mountain. Because to understand why 3I/Atlas is a once-in-a-civilization event, you have to understand everything else that's wrong with it. Everything else that's weird. Everything else that made astronomers around the world cancel their vacation plans and spend the second half of 2025 staring through every telescope they could commandeer. So let's start at the beginning. July 1st, 2025. It's nighttime in Chile's Rio Hurtado Valley. The sky is black and infinite, the Atacama Desert air so dry that moisture is measured in fractions of a millimeter. A 20-inch telescope, not large by modern standards, smaller than some amateur instruments, is doing its nightly scan. This is one of 5 instruments in the ATLAS system, the Asteroid Terrestrial Impact Last Alert System. Its job is planetary defense, watching the sky, looking for rocks that might be on a collision course with Earth, cataloging near-Earth objects, measuring their brightness, their movement, their orbits. On that particular night, the system flags something. A faint point of light, magnitude 17.8, far too dim for the naked eye, barely a whisper in the detector noise. The preliminary designation is forgettable, A11PL3Z, but the software notes something unusual about the way it's moving. The rate of angular motion across the sky, combined with its brightness, suggests an object that's either very close and small or very far and fast. Within 6 hours of the ATLAS detection, astronomers at the Zwicky Transient Facility, a wide-field survey instrument at Palomar Observatory in San Diego County, California, pull their archival data and find the same object in images from June 28th and 29th. More detections are found going back to June 14th, and even earlier, all the way back to May 21st, in data from the Weizmann Astrophysical Observatory in Israel and further ATLAS archives. The object had been passing through our solar system for weeks, hiding in plain sight, or rather, hiding in the dense star fields of the galactic center. 3I/Atlas had been cruising in front of the Milky Way's most crowded stellar real estate, in the direction of the constellation Sagittarius, where the sheer density of background stars makes picking out a faint, moving smudge extraordinarily difficult. But now, with enough data points, enough positions at enough different times, the orbit fitters get to work. And what they find makes jaws drop across every astronomical mailing list on the planet. The orbital eccentricity is 6.141. To appreciate what that number means, you need to understand a little orbital mechanics. Every object in the solar system traces a path described by a conic section, a mathematical shape you get when you slice a cone at various angles. A circle has an eccentricity of 0. An ellipse, the shape most planets follow, has an eccentricity between 0 and 1. Earth's orbit is nearly circular at 0.017. Pluto's is more stretched out at 0.25. An eccentricity of exactly 1 is a parabola, the mathematical boundary between a closed orbit and an open one. Anything above 1 is a hyperbola, an open path, a one-way trip. Oumuamua, the first interstellar object, had an eccentricity of 1.2, just barely hyperbolic. 2I/Borisov was 3.4, clearly unbound, clearly interstellar, but still with a noticeable curve to its path as it swung around the sun. 3I/Atlas has an eccentricity of 6.14. Its path through the solar system is essentially a straight line with the slightest of bends near the sun. It's the fastest, most extreme interstellar trajectory we've ever recorded. This object is screaming through our neighborhood at a speed that no object born in our solar system could possibly achieve. At discovery, it was traveling at approximately 137,000 miles per hour, about 221,000 kilometers per hour, or 61 kilometers per second. As it fell deeper into the sun's gravity well, it picked up speed. By the time it reached perihelion, its closest approach to the sun on October 29, 2025, it was doing 153,000 miles per hour, 68 kilometers per second. And when it leaves, when it climbs back out of the sun's gravity and heads back into the darkness between the stars, it will be going exactly as fast as when it arrived. 137,000 miles per hour. The sun's gravity accelerated it on the way in and will decelerate it on the way out by exactly the same amount. Conservation of energy. You can't cheat physics. And 3I/Atlas will vanish back into the interstellar void at the same speed it emerged from it, carrying whatever secrets it hasn't yet surrendered. The Minor Planet Center made it official on July 2nd. The object was given 2 designations: C/2025 N1 Atlas, following standard cometary naming conventions, and 3I/Atlas, the designation that mattered, the number 3, because it is only the 3rd interstellar object humanity has ever confirmed. The letter I for interstellar, and the name Atlas for the survey system that found it. The news rippled through the astronomical community like a shockwave. Email lists lit up. Telescope time requests flooded into every major observatory on Earth. Within days, the most powerful instruments in the world, and several in space, were being repointed toward this unexpected visitor. Because astronomers understood something immediately. Unlike Oumuamua, which was already on its way out when we noticed it and gave us maybe 11 days of useful observation, 3I/Atlas was inbound. It was still 4.5 astronomical units from the Sun, beyond Jupiter's orbit, and approaching. We had months to study an interstellar object with modern instruments. This had never happened before. Let me set the stage by telling you about the first 2 interstellar visitors, because they matter for understanding why 3I/Atlas hit the astronomical community like a thunderbolt. October 19, 2017. The Pan-STARRS telescope in Hawaii detects a fast-moving object that, after orbit calculations, turns out to be on a hyperbolic trajectory. It's designated 1I/Oumuamua, a Hawaiian name meaning scout or first distant messenger. Oumuamua is weird, deeply, profoundly weird. It's small, maybe 200 meters long, maybe less. Its brightness fluctuates by a factor of 10 every 7 or 8 hours, suggesting an extremely elongated shape, perhaps 6 times longer than it is wide. Some models describe it as cigar-shaped, others as pancake-flat. We don't know because by the time we got serious telescopes on it, it was already receding and too faint for detailed imaging. It has no coma. No tal. No visible outgassing. It looks like a rock, not a comet. And yet, here's the kicker. It's accelerating away from the sun in a way that solar gravity and radiation pressure alone cannot explain. Something is pushing it. Not a lot. A tiny acceleration, measured in billionths of a meter per second squared. But it's there, confirmed in the tracking data. For solar system comets, this non-gravitational acceleration is easily explained by outgassing. Jets of gas escaping from the nucleus create a rocket effect. But Oumuamua showed no gas, no dust, no coma. So what's pushing it? Hypotheses ranged from the plausible it could be outgassing hydrogen, which is invisible to our instruments, built up from cosmic ray bombardment of ice, to the speculative, Loeb's famous proposal that Oumuamua might be a piece of alien technology, a light sail pushed by radiation pressure. We never settled the question. Oumuamua disappeared into the dark too quickly. We'll never see it again. 2 years later, in August 2019, amateur astronomer Gennady Borisov in Crimea spots another fast-moving object that turns out to be interstellar. This one, designated 2I/Borisov, is much more cooperative. It has a coma. It has a tail. It's actively outgassing carbon monoxide. It looks and behaves like a regular comet, just one that came from somewhere else. Borisov is reassuring, in a way. It tells us that the chemistry of other star systems can produce objects recognizably similar to our own solar system's comets. The carbon monoxide abundance is a bit high, but not alarmingly so. The dust properties are broadly familiar. If you showed a spectrum of 2I/Borisov to a planetary scientist without telling them its origin, they might not immediately flag it as exotic. And then 3I/Atlas arrives, and everything changes. The first sign that something is profoundly different comes from the coma. Within days of the July 1st discovery, follow-up observations from the Canada-France-Hawaii telescope on Mauna Kea, the Lowell Discovery Telescope in Arizona, and the Deep Random Survey in Chile all confirm that 3I/Atlas has a diffuse glow around it. Coma. This thing is active, sublimating, outgassing, shedding material. It's a comet, not an asteroid. David Jewitt and Jane Liu, the same astronomers who discovered the Kuiper Belt in 1992, observed 3I/Atlas on July 2nd using the Nordic Optical Telescope and confirm it is clearly active. The coma is there. The object is alive in the cometary sense. But the coma is strange. Its color, as measured by multiple instruments over the following weeks, is red. Not the blue-white you'd associate with a strongly outgassing comet dominated by water vapor and submicron ice grains. Red. A steep reddening in the optical spectrum, with a spectral slope measured at 22.8% per 100 nanometers. This redness tells a story. In planetary science, a red surface usually means organic-rich material. Dark, complex, carbon-bearing molecules, tholins, polycyclic aromatic hydrocarbons, kerogen-like polymers that preferentially absorb blue light and scatter red. This is the color of objects that have been irradiated for a long, long time. Trans-Neptunian objects, those frozen bodies in the outermost reaches of our solar system, often have red surfaces for exactly this reason. Cosmic rays and solar ultraviolet radiation have chemically altered their surface ices over billions of years, building up a crust of dark organic residue. But 3I/Atlas isn't from the outer solar system. It's from the interstellar medium. And the timescale of its exposure to cosmic radiation is measured not in billions of years since the formation of our solar system 4.6 billion years ago, but in the full age of its existence, potentially 10 to 12 billion years. That red surface is a 10 billion year sunburn, written in organic chemistry. Now, July 5th, 2025, near-infrared spectroscopy from Gemini South and the NASA Infrared Telescope Facility on Mauna Kea report the first detection of water ice in 3I/Atlas's coma. Water ice grains, not water vapor, solid particles of ice being dragged out of the nucleus by the force of whatever gas is driving the outgassing. This is important. Water ice grains can only exist in the coma if something else is pushing them out. Water ice at 3+ astronomical units from the sun doesn't sublimate fast enough to drive cometary activity on its own. Something more volatile, something that turns from solid to gas at lower temperatures, has to be doing the heavy lifting. And that something, as we'll learn in August, is carbon dioxide. On July 20th, the Very Large Telescope, the European Southern Observatory's flagship instrument in Chile, consisting of 4 8.2-meter mirrors, detects something unexpected in 3I/Atlas's ultraviolet spectrum: atomic nickel. Glowing nickel atoms, fluorescing in the coma as sunlight excites their electron shells. Nickel in comets was actually discovered relatively recently in 2021, when a team found it in about 20 solar system comets using VLT data. The surprise with 3I/Atlas isn't that nickel is there. It's that nickel is there without iron. In every comet we've ever studied, nickel and iron appear together. They're born together in the hearts of massive stars and scattered together when those stars explode as supernovae. They co-condense into the same mineral grains in protoplanetary disks. They co-sublime when those grains are heated. They are, cosmochemically speaking, inseparable companions. But 3I/Atlas is producing nickel vapor with no detectable iron emission. The VLT data show nickel emission lines growing steadily brighter as the comet approaches the Sun, from 4.4 astronomical units down to 2.85, while iron lines remain stubbornly absent. This has never been seen in any natural object in our solar system. The proposed explanation involves nickel tetracarbonyl, a molecule with the formula NiCO4. This is a volatile organometallic compound that, on Earth, is used industrially in the Mon process, a technique for refining nickel by exploiting the compound's ability to selectively complex with nickel atoms while leaving iron behind. At temperatures around 60 degrees Celsius, nickel reacts with carbon monoxide to form NiCO for gas. The gas can then be decomposed at higher temperatures to deposit pure nickel. The implication is that something similar might be happening naturally on 3I/Atlas. Carbon monoxide, which the comet has in abundance, is reacting with nickel-bearing dust grains near the nucleus, forming nickel tetracarbonyl, which then sublimates away, decomposes in sunlight, and releases free nickel atoms into the coma. The iron, lacking a comparably volatile chemical pathway, stays locked in the solid grains and never reaches the gas phase. This is, to put it mildly, exotic. Loeb, never one to understate, noted in a blog post that this particular chemical pathway was only known to exist in industrially produced nickel alloys. He's not wrong about that fact, but the emphasis on the industrial analogy is misleading. Nature is perfectly capable of running the Mon process without a factory. All you need is nickel, carbon monoxide, and a temperature gradient, and 3I/Atlas has all three. Still, the nickel anomaly underscored something that was becoming increasingly clear. 3I/Atlas is chemically unlike anything we've ever encountered. Every new measurement was returning results that sat outside the known parameter space. And there was another anomaly that defied easy explanation: the anti-tail. Let me explain what a cometary tail normally looks like, because you need to understand the normal before you can appreciate the abnormal. When a comet approaches the Sun, solar radiation heats its nucleus, sublimating ices into gas. That gas streams off the surface and drags dust particles with it. The dust and gas then interact with two forces from the Sun: solar radiation pressure, the physical push of photons, and the solar wind, a stream of charged particles flowing outward at 400 kilometers per second. The result is two tails. The dust tail curves gently away from the Sun, pushed by radiation pressure but lagging behind due to the dust particles' inertia and the comet's orbital motion. This tail is usually whitish or yellowish, reflecting sunlight from the dust grains. The ion tail, composed of charged gas molecules, points almost exactly away from the Sun, blown straight back by the solar wind's magnetic field. This tail is often bluish, from the fluorescence of ionized carbon monoxide. Both tails point away from the Sun. Always, in every comet, in every textbook. This is as fundamental to cometary physics as shadows pointing away from a light source. The Sun pushes material outward. That's how it works. Except 3I/Atlas apparently didn't get the memo. Observations by the Hubble Space Telescope on July 21, 2025, revealed something peculiar in the morphology of the coma. A narrow extension pointing toward the Sun, not away from it. At first, it was subtle, a slight elongation in the sunward direction that could have been dismissed as a data artifact or an asymmetry in the outgassing pattern. But as more observations accumulated, from Keck, from Gemini, from ground-based amateur astronomers wielding serious equipment, the feature became unmistakable. 3I/Atlas had developed an anti-tail, a spike of material extending in the direction of the Sun. Now, anti-tails aren't entirely unheard of in cometary science. They've been seen in a handful of solar system comets, most famously in Comet Arne-Roland in 1957, which shocked observers with a bright forward spike that made front-page news and briefly triggered UFO speculation. But in those cases, the anti-tail was essentially an optical illusion, a geometric projection effect caused by the viewing angle. When the Earth passes through or near the orbital plane of a comet, large dust particles ejected earlier in the orbit can appear to project sunward due to perspective. The particles aren't actually moving toward the sun. They're in the comet's orbital plane and happen to be seen edge-on from Earth's vantage point. For 3I/Atlas, the explanation isn't so clean. The anti-tail was observed from multiple viewing geometries as the Earth-comet angle changed over weeks and months, and it persisted through all of them. The Keck KCWI observations on August 24 showed that the anti-tail appeared not just in white light, which could be reflected dust, but also in nickel and cyanide emission wavelengths. The gas itself was extending sunward. This is deeply strange. Gas molecules in a comet's coma are subject to radiation pressure and the solar wind, both of which push material away from the sun. For gas to appear to extend sunward, something unusual has to be happening. Either the gas is being produced by dust grains that are themselves moving sunward, which raises the question of why dust would be moving toward the sun, or the emission geometry is more complex than a simple radial outflow. One proposed explanation involves large dust grains, particles so massive that solar radiation pressure can't push them away effectively. We're talking about grains perhaps millimeter-sized or larger, for which the ratio of radiation pressure force to gravitational attraction, a quantity called beta, is close to zero. These grains, once released by outgassing, would follow essentially ballistic trajectories, arcing under solar gravity alone, potentially forming structures that project sunward depending on the ejection angles and the comet's orbital geometry. This is consistent with other observations suggesting that 3I/Atlas's dust population is dominated by unusually large particles. The spectral slope measurements, the lack of a strong classical dust tail extending hundreds of thousands of kilometers downwind, and the relatively high ratio of gas to visible dust in the coma all point to a grain population skewed toward hefty chunks rather than the fine submicron particles typical of most solar system comets. But there's another possibility, one that connects to another extraordinary claim about 3I/Atlas. Cryovolcanism, ice volcanoes, erupting on a comet from another star. This concept might sound like science fiction, but it's rooted in well-established planetary science. We've seen cryovolcanism in our own solar system. Saturn's moon Enceladus has geysers that shoot plumes of water ice hundreds of kilometers into space from cracks near its south pole, the famous tiger stripes. Jupiter's moon Europa almost certainly has similar eruptions, driven by the tidal flexing of its ice shell. Even Pluto, that frozen world at the edge of our solar system, has features that may be cryovolcanic in origin, notably a massive mountain called Right Mons that resembles a shield volcano made of ice. The mechanism in all these cases is the same in principle. Subsurface pressure from volatile gases builds up beneath an insulating or sealing layer until it breaches the surface in an explosive or steady-state eruption. On 3I/Atlas, the driving volatile is carbon dioxide. A paper published on the AR-14 preprint server in late 2025, analyzing spectrophotometric data on the comet, argued that 3I/Atlas is showing signatures consistent with cryovolcanic activity. The evidence includes the highly localized, asymmetric jet structures observed by Hubble, the unusual and sometimes erratic brightness variations as the comet approached perihelion, and the anomalous chemical composition, particularly the extreme carbon dioxide abundance, which makes CO2 a much more effective pressurizer than water because it sublimates at lower temperatures and produces higher gas pressures at the same thermal input. Think about what's happening on the nucleus of 3I/Atlas as it approaches the Sun for the first time in its existence. The surface, that 10 billion-year cosmic ray-baked crust, is dark, organic rich. It absorbs sunlight efficiently, converting photons to heat. But that crust is also dense and relatively impermeable, having been compacted by billions of years of cosmic ray bombardment into something approaching amorphous, glassy ice with low porosity. Beneath the crust, there's a reservoir of CO2 ice and other volatiles. As the surface heats up, the sublimation front, the boundary where solid CO2 transitions to gas, migrates downward. But the gas produced at this front can't easily escape through the sealed crust above it. So the pressure builds. Slowly at first, as the comet is still far from the Sun. But as it falls inward, passing 4 AU, 3 AU, 2 AU, the solar flux increases, the temperature rises, and the sublimation rate accelerates. And eventually, something gives. A crack propagates through the crust. A weak point, perhaps a pre-existing fracture from a cosmic ray impact, or a structural flaw in the ice, fails under the mounting gas pressure. And the pressurized carbon dioxide erupts through the surface in a geyser-like blast, carrying dust particles, water ice grains, nickel-bearing compounds, and whatever other material lies in its path. This eruptive, episodic outgassing, as opposed to the gentle, steady sublimation of most solar system comets, could explain several of 3I/Atlas's peculiarities. The large dust grains, violently ejected by high-pressure gas rather than gently lifted by slow sublimation. The anti-tail, material launched at unusual angles by localized jets pointing in various directions, rather than uniformly accelerated by solar radiation pressure. The irregular brightness curve, episodic eruptions producing unpredictable brightening events, rather than the smooth, distance-dependent light curve of a uniformly sublimating body. And here's the key difference between 3I/Atlas and most comets in our solar system. Our comets have been through this before. A typical short-period comet, say, Comet 67P/Churyumov-Gerasimenko, the target of the Rosetta mission, has made hundreds or thousands of perihelion passages. Each passage strips away some surface material and leaves behind a lag deposit of inert dust, particles too heavy to be carried away by the weakening gas flow. Over many orbits, this dust accumulates into a mantle, an insulating blanket that covers the nucleus and moderates its outgassing. The mantle keeps the interior cool, prevents violent pressure buildups, and produces the gentle, predictable behavior we see in most well-studied comets. 3I/Atlas has no dust mantle. It has never passed a star before. Its crust is the cosmic ray process layer, chemically altered, certainly, but structurally very different from a dust mantle built up by repeated thermal cycling. And once the sun's heat breaks through that ancient crust, it hits pristine, volatile-rich ice that has been sealed away from all thermal processing for the comet's entire multi-billion-year existence. The result is potentially explosive, like uncorking a bottle that's been pressurizing for 10 billion years. Some scientists have noted that this lack of a dust mantle also explains why 3I/Atlas brightened so dramatically before perihelion. Most solar system comets, insulated by their mantles, brighten gradually and predictably as they approach the Sunday. 3I/Atlas brightened rapidly. Its inbound brightness curve was steeper than almost any known comet, because there was nothing to moderate the response. Raw ice was being hit by raw sunlight for the first time, and it reacted with enthusiasm. There's one more piece of the pre-perihelion puzzle that ties these observations together: the extended water source. NASA's Swift Observatory, a satellite designed primarily for studying gamma-ray bursts, but equipped with a versatile ultraviolet and optical telescope, observed 3I/Atlas on July 30th and August 1st, 2025. The comet was still about 3.7 astronomical units from the sun. Swift detected the ultraviolet signature of hydroxyl radicals, OH, in the coma. Hydroxyl is a fragment of water, when water molecules are broken apart by solar ultraviolet photons. One of the products is OH, which then fluoresces in the UV. But the spatial distribution of the OH emission was odd. Modeling by Zishi Xing and colleagues at Auburn University suggested that the water wasn't sublimating directly from the nucleus surface. Instead, it was being released from icy grains in the coma, particles of water ice that had been ejected from the nucleus by the much more volatile CO2 outflow, and were then slowly evaporating in sunlight at distances of 4,000 to 10,000 kilometers from the nucleus. This is what planetary scientists call an extended source. The water production is distributed throughout the inner coma rather than concentrated at the nucleus. It means the nucleus isn't really outgassing water on its own, at least not at those heliocentric distances. The water ice is being physically ripped from the surface by carbon dioxide jets, lofted into space as solid grains, and then gently sublimating as the individual grains warm in sunlight. This has implications for the comet's internal structure. It suggests that the near-surface layers are dominated by CO2 ice, with water ice interspersed as a secondary component, perhaps filling pores or existing as inclusions within a CO2 matrix. The water is there, but it's a passenger, not a driver. Carbon dioxide does the heavy lifting. Carbon dioxide cracks the crust. Carbon dioxide launches the jets. Carbon dioxide powers the cryovolcanic eruptions. water comes along for the ride. Think of it like a volcano on Earth. The magma, the molten rock, is the primary driver. But volcanic eruptions also carry water vapor, sulfur dioxide, carbon dioxide, and ash. The magma is the engine. Everything else is cargo. On 3I/Atlas, carbon dioxide is the magma. Water ice is the ash. And the eruptions are cryovolcanic, powered by the sublimation of CO2 ices that have been sealed beneath an irradiated crust for longer than our sun has existed. Post-perihelion, the picture changed dramatically. The JWST December observations showed that water production had increased 20-fold compared to the pre-perihelion SphereX measurements. The extended source mechanism was still operating. Icy grains were still being lofted and sublimating in the coma, but now water was also sublimating directly from the nucleus as the perihelion heatwave had penetrated deeper into the interior. The comet was finally warm enough, for the first time in 10 billion years, for water-ice sublimation to contribute meaningfully to the outgassing budget. And the biggest shock was still to come. August 6, 2025, the James Webb Space Telescope, the most powerful infrared observatory in human history, with a 6.5-meter gold-plated beryllium mirror, cooled to 40 Kelvin, orbiting the L2.1.5 million kilometers from Earth, turns its near-infrared spectrograph toward 3I/Atlas. The NIR-SPEC instrument splits the comet's light into a rainbow spanning from 0.6 to 5.3 micrometers. In that infrared rainbow, each molecule in the coma leaves a fingerprint, a unique pattern of emission lines corresponding to the specific wavelengths of light that molecule radiates when excited by sunlight. The data pipeline runs overnight. By morning, Martin Cordiner at NASA's Goddard Space Flight Center and his team of 13 co-authors are staring at spectra that look like nothing they've seen from any solar system comet. The coma of 3I/Atlas is dominated by carbon dioxide. Not water, carbon dioxide. Let me explain why this is so remarkable. In our solar system, water is king. It's the dominant volatile in virtually every comet we've studied. Water-ice sublimation is what creates the classic coma and tail. Water production rates are the standard metric by which we characterize cometary activity. The entire taxonomy of comets, their classification into long-period, short-period Jupiter family halitype, is built on the assumption that water is the primary driver. Typical solar system comets have a CO2 to H2O ratio somewhere around 0.1 to 0.3. That means for every 10 molecules of water outgassing from the nucleus, you get 1 to 3 molecules of carbon dioxide. Water dominates, CO2 tags along. 3I/Atlas flips that ratio on its head. The measured CO2/H2O mixing ratio is 8.0, plus or minus 1.0, 8 to 1. Carbon dioxide outnumbers water by a factor of 8. This is 4.5 standard deviations above the established trend line for all known long-period and Jupiter family comets. The only solar system comet that comes remotely close is the peculiar object C/2016 R2, sometimes called the Blue Comet, which is so carbon monoxide rich that it's typically excluded from statistical analyses as an outlier. Even C/2016 R2 doesn't reach the CO2/H2O levels of 3I/Atlas. The JWST data are specific and quantitative. At the time of observation, when 3I/Atlas was 3.32 astronomical units from the Sun, the nucleus was emitting approximately 129 kilograms of CO2 per second. 129 kilograms. Every second. That's the mass equivalent of a full-grown adult human being launched into space as carbon dioxide gas every tick of the clock. Alongside the CO2, the comet was releasing 14 kilograms per second of carbon monoxide, about 6.6 kilograms per second of water, and 0.43 kilograms per second of carbonyl sulfide, OCS, a molecule typically associated with volcanic emissions on Earth. JWST also detected water ice grains in the coma, tiny particles smaller than 1 micrometer in diameter, likely amorphous in structure, being dragged from the nucleus by the CO2-driven outflow. The Swift Observatory separately detected hydroxyl radicals, OH, the photodissociation product of water, in ultraviolet emission, suggesting that the water ice grains were sublimating in the coma at distances between 4,000 and 10,000 kilometers from the nucleus. The water wasn't coming directly from the surface. It was being lofted as solid ice by the powerful CO2 jets, then evaporating in sunlight thousands of kilometers away. The spectral maps from JWST showed something else. The CO2 emission was asymmetric, concentrated on the sunward side of the coma. This is consistent with enhanced outgassing from the hemisphere facing the sun, the heated face, which is standard cometary behavior. But the sheer dominance of CO2 over water meant that 3I/Atlas's entire activity cycle was being driven by a different engine than any comet in our experience. In a nice bit of detective work, the JWST team also measured the carbon isotope ratio. Carbon-12 to carbon-13. In the near-nucleus region, they found a lower limit of greater than 77 for the superscript 1 superscript 2c/superscript 1 superscript 3c ratio in CO2, formally consistent with the terrestrial value of 89, but with tantalizing hints that the ratio might be higher. This was an early clue to what would later become the isotopic bombshell of March 2026. Separately, NASA's SPHEREx mission, a new all-sky infrared surveyor that had launched earlier in 2025, confirmed the CO2 finding. SPHEREx detected bright carbon dioxide emission and water ice absorption in its own mid-August observations. While SPHEREx lacked the spectral resolution to detect water vapor and CO directly, its independent confirmation of the CO2 dominance was important. 2 separate space telescopes. Same answer. Carbon dioxide is running the show. The August 25th announcement of the JWST results made headlines worldwide. For the first time, we had a detailed chemical inventory of an interstellar object's outgassing. And that inventory said, "This thing is nothing like our comets." Thomas Puzia, an astronomer at the Pontifical Catholic University of Chile, whose VLT team was simultaneously analyzing the nickel and cyanide emissions, put it best. "We just cracked open the door," he said, "to a whole new world of chemistry that we never had access to before." Let's talk about where that chemistry comes from. Because the CO2 dominance isn't just unusual, it's diagnostic. It tells us something specific about where and how 3I/Atlas formed. In a protoplanetary disk, the rotating disk of gas and dust around a young star, from which planets and comets form, different volatile substances freeze out at different distances from the star. Close in, where it's hot, only refractory materials like silicates and metals can condense. Farther out, where temperatures drop below roughly 170 Kelvin, water ice can form. This boundary is called the water ice line or the snow line. Farther still, beyond where temperatures drop below about 80 Kelvin, carbon dioxide can condense into solid ice. This is the CO2 ice line. And even farther, at temperatures below about 25 Kelvin, carbon monoxide freezes out as well. In our solar system, the CO2 ice line was somewhere around the orbit of Jupiter during the disk's early evolution. Objects that formed well beyond this line, in the Kuiper Belt region or the Oort cloud, would have been enriched in CO2 relative to water, but even then, water typically dominates because it condenses closer to the star where more mass is available. The extreme CO2 enrichment of 3I/Atlas suggests it formed well beyond the CO2 ice line in its parent system, in the deep freeze, far from the parent star, where CO2 ices were abundant and temperatures were crushingly cold. But there's more to it than just formation location. Stephanie Millam, an astrochemist at NASA's Goddard Space Flight Center who worked on the JWST observations, offered another possibility. During its long journey through interstellar space, 3I/Atlas may have developed what she called a cooked shell, a surface layer where galactic cosmic ray bombardment had chemically transformed the original ices. In particular, cosmic rays are known to convert carbon monoxide into carbon dioxide through a well-studied radiation chemistry pathway. This is the cosmic ray processing hypothesis. And in October 2025, a team led by Romain Magillo at the Royal Belgian Institute for Space Aeronomy turned it into a quantitative model. Magillo's paper, posted to the AR-14 preprint server on October 30th, 2025, represents what many consider a paradigm shift in how we think about interstellar objects. The argument goes like this. When a comet or any icy body is ejected from its parent star system and enters the interstellar medium, it's no longer protected by a stellar magnetosphere. It's exposed to the full flux of galactic cosmic rays. High-energy protons, alpha particles, and heavier nuclei accelerated to relativistic speeds by supernova shock waves, pulsar winds, and other violent astrophysical processes. These particles penetrate deep into ice, depositing energy as they go, breaking molecular bonds, liberating atoms, and triggering chains of chemical reactions. Laboratory experiments, some dating back to the late 1990s, by researchers like Reggie Hudson and Marla Moore at NASA Goddard, and by Maria Palumbo's group in Italy, have carefully reproduced these processes. When you irradiate CO ice with high-energy protons under vacuum at low temperatures, several things happen. First, the CO molecules are dissociated. Carbon and oxygen atoms are liberated, along with excited molecular fragments. These fragments recombine, but not necessarily into the same molecules they started as. Carbon monoxide plus atomic oxygen becomes carbon dioxide. Two CO molecules can react to form C2O2, which rearranges into CO2 plus solid carbon. Simultaneously, complex organic molecules begin to form. Carbon atoms link together. Carbon-oxygen chains grow. Eventually, you develop a dark, refractory, organic-rich residue, a carbonaceous crust that absorbs blue light and looks red in the visible spectrum. Sound familiar? It should. Red spectral slope. Check. CO2 enrichment. Check. Ongoing CO release from the breakdown of irradiated organics. Check. Magillo's team used Monte Carlo radiation transport simulations to estimate how deep galactic cosmic rays can penetrate into a cometary nucleus over billions of years. The answer, about 15 to 20 meters. Below that depth, the ice is shielded. The cosmic rays can't reach it. It remains pristine. And here's the critical calculation. The erosion rate of 3I/Atlas's nucleus, the rate at which material is being lost through sublimation and outgassing, is measured from the actual mass loss rates observed by JWST and other instruments. When you compare the total amount of material 3I/Atlas is expected to lose during its passage through the solar system to the depth of the cosmic ray process zone, you find that the comet will only shed about 15 to 20 meters of surface material. It will never dig deep enough to reach the pristine interior. What we are seeing, all the CO2, all the CO, all the red organics, all the exotic chemistry, is the cosmic ray-baked rind. The 10 billion-year patina of galactic radiation chemistry. The outermost shell of an object that was chemically rewritten during its impossibly long journey between the stars. Magillo's team put it bluntly, rather than being pristine messengers from distant planetary systems, interstellar objects may instead carry signatures of processed material shaped by billion-year scale cosmic ray exposure. This is both thrilling and sobering. Thrilling because it means we can study cosmic ray chemistry in situ. We have a natural laboratory floating through our solar system. Sobering because it means the original chemistry of 3I/Atlas's parent system, the information we really wanted, is locked away beneath a layer of transformed material that we can't access. Or so we thought, until the methane showed up. December 15 and 27, 2025. 3I/Atlas has passed perihelion. It survived its closest approach to the Sun on October 29th without fragmenting, no small feat for an ancient, well-irradiated nucleus. It's now heading outbound, past the orbit of Mars, fading but still active. JWST points its MIRI instrument, the mid-infrared instrument, capable of observing wavelengths from 5 to 28 micrometers, at the receding comet. MIRI sees deeper into the infrared than NIR spec, accessing molecular vibrations and rotational transitions that are invisible at shorter wavelengths. The resulting spectra are extraordinary. They show water vapor at 5.8 to 7 micrometers, carbon dioxide emission around 15 micrometers, including both the primary band and its associated hot bands, vibrational transitions that are only excited at elevated temperatures, indicating gas freshly released from the warm nucleus. A forbidden transition of atomic nickel at 7.507 micrometers, forbidden in the quantum mechanical sense, meaning it's a transition with a very low probability that only becomes observable when nickel atoms spend a long time in a low-density environment without collisions to de-excite them. And there, at 7.6 micrometers, something new. Something that hadn't been seen in either the August JWST observations or the SphereX data. Methane. Say hat? The simplest hydrocarbon. A carbon atom with 4 hydrogen atoms. The first detection of methane in any interstellar object. Ever. The methane production rates are measured at 2 epochs. On December 15th and 16th, when 3I/Atlas is at 2.2 astronomical units from the Sun, methane accounts for 13.7% of the water production rate. 12 days later, on December 27th, at 2.54 AU, it's jumped to 27%. The methane is increasing while the water is declining. This temporal pattern is the key. Methane is a hypervolatile. Its sublimation temperature is far below that of water and even below that of carbon monoxide. In a pristine nucleus, methane should be the first thing to sublimate as the comet approaches the Sun. It should show up early, when the comet is still far out and cold, and decline as the methane-rich surface layers are exhausted. But 3I/Atlas did the opposite. No methane was detected before perihelion. It only appeared after. The interpretation, as laid out by Kordener's team in their January 2026 paper, is that methane was depleted from the comet's outer layers, either during formation or during the billions of years of cosmic ray processing, and survived only in the deeper, unprocessed interior. As the Sun's heat penetrated past the irradiated crust, it reached layers that had been shielded from cosmic rays. Layers where pristine ices, including methane, had been preserved since the comet formed. This is profoundly important. It means that the methane and the isotopic ratios in that methane may represent genuine primordial material from 3I/Atlas's birth environment. Not cosmic ray processed rind. Not galactic patina. The real stuff, the original recipe, and the isotopic data from that methane would turn out to be staggering. Before we get to the isotopes, the truly cosmic revelation, let's pause and appreciate the scale of the observing campaign that humanity threw at this object. 3I/Atlas wasn't just studied by a few telescopes. It was observed by essentially every major astronomical asset available to the human species. On the ground, the Very Large Telescope in Chile, the Gemini North and Gemini South telescopes, the Keck Observatory in Hawaii, the Nordic Optical Telescope on La Palma, the Lowell Discovery Telescope in Arizona, the Southern African Large Telescope, the Subaru Telescope on Mauna Kea, the James Clerk Maxwell Telescope also on Mauna Kea, which detected hydrogen cyanide at submillimeter wavelengths, the Gran Telescopio Canarias, the Canada-France-Hawaii Telescope, dozens of smaller professional and amateur instruments worldwide. In space, the James Webb Space Telescope, the Hubble Space Telescope, which provided the sharpest visible light images and constrained the nucleus size, NASA's TESS satellite, which performed extended photometric monitoring, the Swift Observatory, which detected hydroxyl emission in ultraviolet, the Spherex Survey Telescope, NASA's Parker Solar Probe, which caught the comet with its wide-field imager during the perihelion solar conjunction window, the SOHO spacecraft at the L1 point, which captured the comet transiting through its coronagraph field of view, and JAXA's XRISM X-ray Observatory, which detected diffuse X-ray emission around the nucleus, the first X-ray detection of any interstellar object. From Mars, the Mars Reconnaissance Orbiter, using its HiRISE camera to photograph the comet from 18.6 million miles. The ExoMars Trace Gas Orbiter and Mars Express, both redirected to observe the visitor during its closest approach to Mars on October 3rd. And, remarkably, the Perseverance rover, a six-wheeled robotic geologist sitting on the floor of Jezero crater on the Martian surface, which looked up with its Mastcam-Z camera and photographed 3I/Atlas as a faint smudge in the Martian sky. The first observation of an interstellar object from the surface of another planet. From deep space, NASA's Lucy spacecraft, en route to Jupiter's Trojan asteroids, captured images in September 2025 from 240 million miles away, revealing the coma and a tail. ESA's JUICE spacecraft, heading for Jupiter's icy moons, turned 5 instruments toward 3I/Atlas in November 2025, just days after perihelion, catching the comet in a highly active state. The data downlink wasn't completed until February 2026. Even the Vera C. Rubin Observatory got involved, coordinating observations with Breakthrough Listen for concurrent optical and radio monitoring. This was the largest coordinated astronomical campaign ever directed at a single solar system visitor. More instruments, more wavelengths, more platforms, more data than any comet has ever received. And it all happened within a window of months, from discovery in July to the comets fading below detection thresholds in early 2026. We threw everything we had at 3i/Atlas, and it rewarded us with data that will fuel doctoral theses for decades. Now, the perihelion passage and its aftermath. October 29, 2025. 3i/Atlas passes closest to the Sun at 1.36 astronomical units between the orbits of Earth and Mars. At that distance, the solar flux is about 54% of what Earth receives. Not blistering, Mars gets roughly the same, but far more intense than anything 3i/Atlas has experienced in perhaps 10 billion years. During the 3-week period around perihelion, the comet is too close to the Sun to be observed from Earth. It's in solar conjunction, hidden by the glare of our star. But spacecraft in advantageous positions catch glimpses. Parker Solar Probe's WISPR camera tracks it from October 18th to November 5th. SOHO's coronagraph detects it as a faint brightening. And from Mars, much closer to the comet's perihelion path, ESA's orbiters watch the fireworks. When 3i/Atlas emerges from solar conjunction in November and December, the changes are dramatic. First, the color. Pre-perihelion, the comet was red, organic-rich crust, cosmic ray processed surface. Post-perihelion, images from Gemini North's GMOS instrument on November 26th reveal a striking transformation. The comet has turned green. Not subtle green, vivid green, the color of diatomic carbon C2 molecules, fluorescing in sunlight. This green glow is a familiar signature in solar system comets. Diatomic carbon forms when larger organic molecules in the coma are photodissociated by solar ultraviolet radiation. But the shift from red to green tells a story of erosion. The ancient organic crust has been stripped away. Deeper, fresher ices that haven't been irradiated for billions of years, are now being exposed to sunlight for the first time. The comet is literally shedding its ancient skin and revealing what lies beneath. Second, the activity level. SphereX reobserved 3i/Atlas in December 2025 and found a comet full-on erupting into space. According to the mission team's blog update, the water ice absorption signature that had been prominent in pre-perihelion data had largely disappeared, replaced by gas phase emissions from water vapor, 20 times brighter than before, carbon dioxide, carbon monoxide, cyanide, and organic compounds in the 3 to 4 micrometer band. A weak, pear-shaped dust tail had developed, pointing roughly anti-sunward, consistent with large dust grains being pushed by radiation pressure. Third, the rotation. And this is perhaps the most physically dramatic change of all. Pre-perihelion ground-based observations in July 2025 measured 3i/Atlas's rotation period at approximately 16.16 hours. A leisurely, unhurried spin, one rotation roughly every 2/3 of an Earth day. By January 2026, Hubble photometry and test-light curve data tell a very different story. The rotation period has dropped to approximately 7.1 hours. In the space of 6 months, the nucleus has more than doubled its spin rate. This spin-up is caused by outgassing torques. When jets of gas erupt asymmetrically from a nucleus, from a crack here, a freshly exposed patch of ice there, they don't just push the comet in one direction. They apply a torque, a rotational kick. For 3i/Atlas, the intense perihelion activity created forces that spun the nucleus faster and faster, like a top being wound up by repeated flicks of the fingers. Hubble images of the post-perihelion coma structure show 3 symmetric mini-jets separated by about 120 degrees, each wobbling back and forth by roughly 20 degrees with the 7-hour rotation period. The rotation axis appears to be nearly aligned with the comet-sun direction, within about 20 degrees, creating a cone-like sweep pattern as the jets trace spirals into space. This rapid spin-up raises a real concern. Could the nucleus tear itself apart? Cometary nuclei are typically held together by very weak forces. The tensile strength of a comet is comparable to that of a snowball. If the rotation period drops below a critical threshold, centrifugal force exceeds gravity plus cohesion, and the nucleus fragments. This happened before. Comet Shoemaker-Levy 9 broke apart from tidal forces, and several periodic comets have disintegrated from rotational spin-up. As of the latest observations, 3i/Atlas appears intact. But it's spinning dangerously fast. and the question of whether it will survive long enough to provide continued observations as it recedes is an open one. Fourth, the thermal inertia asymmetry. The comet's peak water production didn't coincide with perihelion. It came about a week later, around November 6, 2025. This delay is a textbook signature of thermal lag. The nucleus acts as a thermal reservoir, absorbing heat slowly and continuing to outgas even after the solar flux has begun to decline. But the magnitude of the asymmetry in 3I/Atlas is extreme. The inbound brightness increase followed a steep power law, proportional to roughly the inverse 5.9 power of heliocentric distance. The outbound decline follows a much shallower inverse 3.3 power. This means 3I/Atlas stayed active far longer on the way out than simple solar heating models predict. The most likely explanation is that the comet's interior, never before heated by a star, represented an enormous reservoir of volatile ices. Once the heat wave from perihelion penetrated past the process surface layers and reached pristine ice, it unlocked a flood of sublimation that persisted well into the post-perihelion trajectory. The interior was encountering warmth for the first time in its existence, and it was responding enthusiastically. Let me take you to Mars for a moment, because the encounter between 3I/Atlas and the Red Planet on October 3, 2025, was one of the most remarkable episodes in the entire story, and it happened while we on Earth couldn't even see the comet. On that date, 3I/Atlas passed within 29 million kilometers of Mars, about 0.194 astronomical units. That's closer than any planet-comet encounter in our solar system in recent memory for an interstellar object. Mars had a front-row seat to a visitor from another star. And Mars has eyes. NASA's Mars Reconnaissance Orbiter turned its HiRISE camera, the high-resolution imaging science experiment, capable of resolving surface features less than a meter across on Mars, toward the incoming comet. At the distance of the encounter, HiRISE's pixel resolution for 3I/Atlas was roughly 30 kilometers. That's about 3 times sharper than the best Hubble or Keck images taken from Earth. For the first time, we had the possibility of seeing structure within the coma at a level of detail impossible from our home planet. Simultaneously, ESA's Mars Express Orbiter and the ExoMars Trace Gas Orbiter, 2 European spacecraft circling Mars on different orbits, redirected their instruments toward the comet. Mars Express carries a high-resolution stereo camera and a spectrometer. TGO has its own suite of atmospheric and spectral instruments. Both were tasked with capturing whatever they could during the brief window when 3I/Atlas was geometrically accessible from Martian orbit. The Mars-based observations had a unique advantage beyond proximity. From Mars, the viewing angle to 3I/Atlas was substantially different from the angle seen from Earth. This parallax, the difference in perspective between 2 widely separated observation points, allows astronomers to construct 3-dimensional models of the coma structure. Features that appear ambiguous from a single vantage point can be disambiguated when seen from 2. And then there was Perseverance, the rover, trundling across the ancient lakebed of Jezero crater on the Martian surface, received commands to look up. On October 4th, using its Mastcam-Z camera, a pair of zoomable stereo cameras mounted on the rover's mast, Perseverance captured a sequence of images showing 3I/Atlas as a faint, diffuse smudge against the Martian sky. It was the first time any interstellar object had been observed from the surface of another world. A robot on Mars, photographing a comet from another star. If that doesn't give you chills, check your pulse. The Mars encounter also gave us our first data on how the solar wind, which is somewhat different at Mars's distance compared to Earth's, interacts with 3I/Atlas's coma. The Meerkat radio array in South Africa, observing in the 900 to 1600 MHz band, detected signatures of hydroxyl, OH, in the comet's radio emission. Hydroxyl is the dissociation product of water, and its detection at radio wavelengths provides an independent measure of the water production rate, complementing the infrared measurements from JWST and the ultraviolet detections from SWIFT. The Meerkat observation was part of a broader Breakthrough Listen campaign but had dual scientific purpose. While the BLUS Breakthrough Listen user-supplied equipment backend searched the data for narrowband artificial signals and found none, at a sensitivity equivalent to the power output of a mobile phone at the comet's distance, the astrophysical front end captured the hydroxyl line emission, confirming that water was actively being produced and dissociated in the coma throughout the pre-perihelion approach. There was one more act in the encounter drama. Jupiter. 3I/Atlas's trajectory brought it within 0.358 astronomical units, about 54 million kilometers, of Jupiter on March 16, 2026. This is close enough that NASA's Juno spacecraft, currently in orbit around the gas giant, was theoretically within observation range. Juno carries a suite of instruments designed for studying Jupiter: a near-infrared spectrometer, a magnetometer, a microwave radiometer, and a camera called JunoCam. Several of these could, in principle, observe 3I/Atlas during the close encounter. The near-infrared spectrometer could analyze the comet's surface composition. The magnetometer might detect any interaction between the comet's gas coma and the local interplanetary magnetic field. JunoCam could capture resolved images from a perspective impossible from Earth. Astrophysicist Marshall Eubanks calculated that with a trajectory correction maneuver in mid-September 2025, a burn of Juno's thrusters to adjust its orbit, the spacecraft could potentially be directed toward an even closer flyby of 3I/Atlas as it passed near Jupiter. The proposal was bold. Delay Juno's planned end-of-mission plunge into Jupiter's atmosphere in favor of this unprecedented intercept. The idea generated enormous excitement in the planetary science community. A spacecraft flyby of an interstellar object, even a distant one, would represent a quantum leap in the data we could collect. Resolved imaging, close-range spectroscopy, in situ particle and field measurements. This was the kind of opportunity that might not come again for decades. But practical realities intervened. Juno is old. It's been in the harsh radiation environment of Jupiter since 2016. Its instruments have degraded. Its fuel supply is limited. Redirecting the spacecraft would introduce mission risk and require approval through a complex decision-making process involving multiple NASA divisions. As of early 2026, the outcome remains uncertain. Whether Juno attempted the observation, and with what results, is still being evaluated. The near miss with Juno underscores a frustrating truth about interstellar visitors. They arrive unannounced, on unpredictable trajectories, and we almost never have the right spacecraft in the right place at the right time. The Comet Interceptor concept, a spacecraft designed to wait at L2 until a suitable target is found and then sprint to intercept it, is specifically intended to solve this problem. But Comet Interceptor won't launch until 2029 at the earliest. For 3I/Atlas, we had to make do with what was already in space. And what was already in space, it turns out, was more than anyone expected. The sheer number of spacecraft that contributed observations, from Parker Solar Probe to Perseverance, from Lucy to JUICE, from SOHO to XRISM, speaks to the depth and redundancy of humanity's presence in the inner solar system. We may not have a dedicated interstellar interceptor yet, but we have a network of scientific assets that can be repurposed on short notice. The next interstellar visitor will find an even better prepared humanity. There's one more physical detail about 3I/Atlas that I haven't mentioned yet, and it's crucial for understanding the comet's mass and structural integrity. Non-gravitational acceleration. Like Oumuamua before it, 3I/Atlas deviates slightly from the trajectory predicted by gravity alone. As gas jets erupt from the nucleus, they produce a rocket-like thrust that gently pushes the comet off its purely gravitational path. By carefully tracking 3I/Atlas's position over weeks and months, and comparing the observed trajectory to what gravity alone would produce, astronomers can measure this non-gravitational acceleration with high precision. The result, 3I/Atlas experienced a peak non-gravitational acceleration of approximately 89.3, plus or minus 4.6, times 10 to the minus 9th astronomical units per day squared. That's tiny in absolute terms, far too small to notice by eye in any single observation. But over days and weeks, it accumulates, shifting the comet's position by measurable amounts. Here's why this matters. If you know the non-gravitational acceleration and you know the mass loss rate from the JWST gas production measurements, you can calculate the mass of the nucleus. It's basic Newtonian mechanics. The thrust equals the mass flow rate times the exhaust velocity, and the acceleration equals the thrust divided by the nucleus mass. When you run the numbers, the implied nucleus mass is roughly 4.4 times 10 to the 10th kilograms, about 44 billion kilograms or 44 million metric tons. For a comet nucleus with a typical density of 200 to 600 kilograms per cubic meter, comets are porous, fluffy objects, more snowdrift than snowball. This mass corresponds to a diameter of about 500 to 750 meters. This is consistent with Hubble's post-perihelion imaging, which resolved the nucleus and measured an effective diameter of about 2.6 kilometers, though that measurement depends on assumptions about the nucleus's albedo, surface reflectiveness, and shape. The mass estimate from non-gravitational acceleration provides an independent constraint that agrees with the imaging within the uncertainties. The bottom line, 3I/Atlas is big. Not enormous by cometary standards. Some Oort cloud comets are tens of kilometers across, but solidly in the mid-range. And importantly, it's about 40 times more massive than 2I/Borisov and at least 20,000 times more massive than Oumuamua. The interstellar objects we found span an enormous range of sizes, from Oumuamua's tiny, mysterious sliver to 3I/Atlas's substantial ice mountain. This has implications for the population statistics of interstellar objects. If 3I/Atlas, a roughly kilometer-sized body, can be detected by Atlas at magnitude 17.8 when it's 4.5 AU from the Sun, then there should be a vastly larger population of smaller objects that we're missing entirely. The current detection rate of about one interstellar object every few years almost certainly represents just the tip of the iceberg. The true flux of interstellar material through the inner solar system is probably orders of magnitude higher. And then came the isotopes. December 22nd and 23rd, 2025. Just days after 3I/Atlas's closest approach to Earth, JWST trains its NIRSpec instrument on the receding comet one more time. This time, the goal is different. The team isn't looking for new molecules. They're looking for isotopologues, variants of known molecules where one atom has been replaced by a heavier or lighter isotope. Specifically, they're looking for HDO, water in which one hydrogen atom has been replaced by deuterium. And they're looking for superscript 1 superscript 3CO2 and superscript 1 superscript 3CO, carbon dioxide and carbon monoxide, containing the heavy carbon isotope carbon-13 instead of the usual carbon-12. The results, published as a preprint on AR-14 in early March 2026 and simultaneously submitted to the journal Nature, are nothing short of historic. The deuterium to hydrogen ratio in 3I/Atlas's water is 0.95%, plus or minus 0.06. In solar system comets, this ratio typically ranges from 0.01 to 0.05%. Earth's oceans are at 0.016%. The Vienna Standard Mean Ocean Water, the international reference standard, sits at 0.0156%. 3I/Atlas has more than 10 times the deuterium concentration of any comet ever measured. More than 60 times the concentration in Earth's oceans. Within the solar system, only the atmosphere of Venus has a higher D/H ratio, and that's due to an entirely different process, preferential loss of hydrogen over deuterium from the upper atmosphere over 4 billion years of solar wind stripping. The D/H ratio in 3I/Atlas is 12 standard deviations above the mean for all protostars in the galaxy. 12 sigma. In a field where 5 sigma gets you a Nobel Prize, this is as close to certainty as science gets. But it gets even more extreme. The JWST MIRI observations from December also measured the deuterium content in 3I/Atlas's methane. The D/H ratio in CH3D, deuterated methane, is 3.31%, plus or minus 0.34, 3.3%. That's more than 3 times the deuterium enrichment in its water. And it's only the second time CH3D has ever been securely detected in any comet. The first was through in situ measurements by the Rosetta spacecraft at Comet 67P/Churyumov-Gerasimenko. These are not subtle anomalies. These are screaming signals. What produces such extreme deuterium enrichment? The answer lies in low-temperature chemistry, specifically in the quantum mechanics of isotope exchange. At very low temperatures, below about 30 Kelvin, or minus 243 degrees Celsius, the energy differences between hydrogen bonds and deuterium bonds become significant relative to the thermal energy of the environment. A reaction that substitutes deuterium for hydrogen in a molecule can be slightly energetically favorable at these temperatures, because the heavier isotope forms a slightly stronger bond due to its lower zero-point energy. In warmer environments, these differences are swamped by thermal energy and the fractionation disappears. But in the ultra-cold cores of molecular clouds, the dense, dark regions where stars and planets are born, the fractionation can be dramatic. The process begins in the gas phase, where the reaction H3 plus HD H2D plus H2 is favored at low temperatures, producing the reactive ion H2D. This ion then participates in a cascade of reactions that transfer deuterium into molecules like water and methane, both in the gas phase and on the surfaces of dust grains. The colder the cloud, the more efficient the fractionation. The longer the material stays cold, the more deuterium gets incorporated. 3I/Atlas formed in an environment so cold below 30 Kelvin, and so quiescent that this fractionation reached unprecedented levels. An environment that existed in the early Milky Way, during or shortly after the period of peak star formation known as cosmic noon, when the galaxy was between 2 and 4 billion years old. And the carbon isotopes nail down the timing even more precisely. The superscript 1 superscript 2c / superscript 1 superscript 3c ratio in 3I/Atlas is significantly higher than anything measured in our solar system, in nearby interstellar clouds, or in protoplanetary disks around young stars. Values range from about 140 to about 190, depending on the molecule and the observing epoch. For reference, the terrestrial ratio is about 89. The ratio in our local interstellar medium is about 68. Why does this matter? Because superscript 1 superscript 3c is produced by the CNO cycle in the cores of stars. It's a byproduct of stellar nucleosynthesis. Over the lifetime of the galaxy, as generations of stars fuse hydrogen into helium and beyond, they enrich the interstellar medium with superscript 1 superscript 3c. The total superscript 1 superscript 3c abundance in the galaxy goes up over time. So the superscript 1 superscript 2c / superscript 1 superscript 3c ratio goes down over time. A high ratio, lots of superscript 1 superscript 2c, relatively little superscript 1 superscript 3c, means the material formed when the galaxy was young, before many generations of stars had enriched the medium with heavy carbon. When you plug the measured superscript 1 superscript 2c / superscript 1 superscript 3c ratios into standard models of galactic chemical evolution, models that track how isotope ratios change as the galaxy ages and recycles its gas through stellar populations, you get an age estimate: 10 to 12 billion years. 3I/Atlas formed roughly 10 to 12 billion years ago, in a metal-poor environment, at temperatures below 30 Kelvin, in a protoplanetary disk around a star that belonged to one of the earliest generations of planet-forming systems in the Milky Way. The universe is 13.8 billion years old. The Milky Way began assembling around 13 billion years ago. 3I/Atlas was born when the galaxy was 1 to 3 billion years old. It is a surviving fragment of one of the very first planetary systems the Milky Way ever produced. And we just watched it fly past our window. Let me put all of this together, because the story of 3I/Atlas is not just a catalog of anomalies. It's a narrative, a 10 billion year narrative that spans the history of our galaxy. Chapter 1, The Formation. Between 10 and 12 billion years ago, in the thick disk of the young Milky Way, a star is born. It's not a star like our sun. It's an older population star, forming from gas that hasn't been enriched by many prior generations of stellar nucleosynthesis. The gas is relatively metal-poor. Around this star, a protoplanetary disk of gas and dust condenses. In the outer reaches of that disk, far from the young star's warmth, temperatures hover below 30 Kelvin. In that extreme cold, ices form on dust grains. Water ice, carbon dioxide ice, carbon monoxide ice, methane ice, and the frigid temperatures drive quantum mechanical fractionation, pumping these ices full of deuterium to levels that will seem alien when measured billions of years later. Somewhere in those frozen outer reaches, a comet accretes. A body 2 to 3 kilometers across, a mountain of ice and rock and organics, gravitationally assembled from the scraps of planet formation. This comet is one of trillions forming around this ancient star. Chapter 2, The Ejection. At some point, perhaps hundreds of millions of years after formation, perhaps sooner, the comet's orbit is disturbed. Maybe a giant planet in the system migrates inward or outward, scattering smaller bodies. Maybe a passing star disrupts the outer disk. Whatever the cause, the comet receives a gravitational kick that sends it flying out of its parent system and into the interstellar void. This is not unusual. It happens in every planetary system. The formation of giant planets is inherently messy. Jupiter, in our own solar system, ejected trillions of comets from the Sun's protoplanetary disk into interstellar space. The Oort cloud that surrounds our solar system is just the fraction that didn't quite make it out, the ones that were captured at the gravitational margin. Chapter 3: The Journey. For the next 10 billion years, the comet drifts through the Milky Way. It orbits the galactic center on a tilted, bobbing path, rising above and plunging below the plane of the disk. It passes through spiral arms, crosses interstellar voids, encounters the diffuse glow of galactic cosmic rays. And those cosmic rays, relentlessly year after year, century after century, eon after eon, irradiate its surface. Let me try to make you feel the scale of this journey. 10 billion years. The Sun is 4.6 billion years old. 3I/Atlas was already ancient when the Sun was born. While our solar system was assembling itself from the collapse of a molecular cloud, while Jupiter was accreting gas, while the Earth was being assembled from collisions of molten protoplanets, while the Moon was being formed in a titanic impact, 3I/Atlas was already out there, drifting, old, cold, a piece of forgotten cosmic infrastructure from the Milky Way's first major construction phase. During those 10 billion years, the Milky Way itself changed almost beyond recognition. When 3I/Atlas was ejected from its parent system, the galaxy was still accreting smaller satellite galaxies, growing through mergers and cannibalism. The thick disk, the dynamically hot stellar population to which 3I/Atlas belongs, was being stirred and heated by these interactions. Spiral arms were forming, dissolving, reforming. Star formation was declining from its cosmic noon peak, but was still vigorous. 3I/Atlas passed through all of this. The September 2025 study by Yang Guo and collaborators attempted to trace the comet's path backward through the galaxy, comparing its velocity to the known positions and motions of nearby stars. They found that 3I/Atlas may have passed within 1 parsec, about 3.3 light-years, of 25 known stars in just the past 10 million years. 10 million years is a blink, less than 1,000th of the comet's total travel time. If the encounter rate has been roughly similar over its entire history, 3I/Atlas has passed close to hundreds of thousands of stars. Some of those encounters may have been close enough to modify the comet's trajectory. Gravitational slingshots off passing stars can change an interstellar object's velocity by a few kilometers per second, bending its path through the galaxy. Some encounters may have been close enough to briefly warm the comet's surface. A red dwarf passing within a few hundred AU could raise surface temperatures enough to sublimate the most volatile ices, potentially stripping methane from the outer layers while leaving the deeper interior cold. This is actually one proposed explanation for why methane was depleted from 3I/Atlas's outer layers but preserved in its interior. Close stellar encounters over 10 billion years could have selectively removed the most volatile surface ices, a kind of thermal winnowing. The cosmic ray-processed crust then sealed the remaining interior from further loss. The methane was buried, locked, and preserved until our sun's warmth finally dug deep enough to release it. The outer 15 to 20 meters of the nucleus were slowly transformed by cosmic ray bombardment over those eons. Carbon monoxide was converted to carbon dioxide. Complex organic molecules were synthesized from simpler precursors. A dark, reddish, refractory crust of irradiation-produced organics built up, absorbing blue light and scattering red. The original water ice was compacted into a dense, amorphous form with low diffusivity and high thermal conductivity. Irradiated ice has different physical properties from ordinary crystalline or amorphous ice, becoming harder and more resistant to sublimation. The methane, being hypervolatile, was selectively depleted from the uppermost layers, leaving behind a methane-poor, CO2-rich surface that would eventually fool us into thinking the whole comet was CO2-dominated. But deep inside, below 20 meters, the pristine ices remained untouched, shielded by the very crust that the cosmic rays created. A sealed vault of primordial chemistry, locked away for 10 billion years. the deuterium-rich water, the deuterium-rich methane, the original carbon isotope ratios, the chemical memory of an ancient protoplanetary disk, written in molecules and sealed in ice, waiting for a star to read it. Chapter 4. The Arrival. In 2025, this ancient traveler enters the solar system. It approaches from the direction of Sagittarius, near the galactic center, on a nearly straight-line trajectory with an eccentricity of 6.14. It has no idea what awaits it. No intention, no purpose. It's just a piece of ice following a gravitational path. And we see it. A 20-inch telescope in Chile picks up its faint glow. Within hours, the orbit is calculated. Within days, the world's telescopes are mobilized. Within weeks, the most powerful space observatories ever built are scrutinizing its composition atom by atom, molecule by molecule, isotope by isotope. Chapter 5. The Revelation. The comet's outer layers, the cosmic ray processed rind, tell us about the interstellar medium, about radiation chemistry over billion-year timescales, about how galactic cosmic rays transform ice. But the deeper layers, the methane that appears after perihelion, the deuterium signatures that shatter all records, tell us about the comet's birthplace, about conditions in the young Milky Way, about a protoplanetary disk so cold and so metal-poor that its ices carry a chemical fingerprint the modern galaxy has erased. Chapter 6. The Departure. And now the comet is leaving, heading outbound past Jupiter, accelerating back toward interstellar speed. By the time you hear this, it will already be beyond the reach of most ground-based telescopes, fading into the dark, returning to the void it spent 10 billion years traversing. It will never come back. There's a philosophical weight to that last fact that deserves a moment. We live on a single planet, orbiting a single star, in a single galaxy, in a universe that's been expanding for nearly 14 billion years. Our ability to reach out and touch other star systems is, at present, zero. We can send radio signals. We can launch probes that will take tens of thousands of years to reach the nearest star. We can dream. But the universe occasionally sends things to us. Objects that formed around other stars in other eras under other conditions. And for a brief window measured in months, not decades, these objects are close enough to study. 3I/Atlas gave us that window. We used it. We learned things that no one predicted. The deuterium enrichment, the methane emergence, the cosmic ray processing, the carbon isotope ages, the nickel without iron puzzle, the cryovolcanism, the spin-up, the color change from red to green. Each of these discoveries will generate years of follow-up research, theoretical models, laboratory experiments, comparative studies with future interstellar visitors. The data collected during 3I/Atlas's passage will be mined for insights for a generation. And there's more to come. ESA's JUICE data from November 2025 are still being analyzed. The Juno spacecraft at Jupiter may attempt observations as 3I/Atlas passes within about 54 million kilometers of Jupiter in March 2026. Post-perihelion JWST data from December 2025 are still being reduced and interpreted. We are not finished with 3I/Atlas. Even as the comet fades, the data it left behind continues to illuminate. But looking forward, what comes next? The Vera C. Rubin Observatory in Chile is now operational with the Legacy Survey of Space and Time (LSST). And this changes everything about how we find interstellar visitors. To appreciate what Rubin represents, think about the telescopes that found our 3 interstellar objects. Oumuamua was found by Pan-STARRS, a 1.8-meter telescope, scanning the sky in relatively shallow exposures, looking primarily for near-Earth asteroids. It caught Oumuamua only after the object had already passed perihelion and was outbound, giving astronomers maybe 2 weeks of useful observation. 2I/Borisov was found by an amateur astronomer with a half-meter telescope, a remarkable feat of skill, but one that happened late enough in the comet's approach that the window for study, while better than Oumuamua, was still limited. 3I/Atlas was caught by a 20-inch Atlas telescope, again a relatively modest instrument, and even then, the comet had already been in the solar system for weeks, hiding against the dense star fields of the galactic center before anyone noticed it. The Rubin Observatory is a different animal entirely. Its 8.4-meter primary mirror, larger than any of the Discovery telescopes by a factor of 4 or more, feeds a 3.2 gigapixel camera, the largest digital camera ever built. This camera covers a field of view of 9.6 square degrees, about 40 times the area of the full moon, in a single exposure. The telescope is designed to survey the entire visible southern sky every 3 nights, repeatedly, automatically, with a depth reaching 24th magnitude. Magnitude 24. For reference, 3I/Atlas was discovered at magnitude 17.8. That's more than 6 magnitudes fainter, which translates to a factor of about 250 in brightness. Rubin will routinely detect objects 250 times fainter than 3I/Atlas was at discovery. That means either much smaller objects at the same distance or same-sized objects much farther away. Simulations by the Rubin team predict that LSST will detect somewhere between 1 and several dozen interstellar objects over its 10-year primary mission. Some of these may be found at 5 or 6 astronomical units from the Sun, well beyond Jupiter, giving us months or even years of warning before they reach the inner solar system. Months to mobilize telescopes. Months to coordinate observation campaigns. Months to, perhaps, redirect a spacecraft. And that's where Comet Interceptor comes in. The European Space Agency's Comet Interceptor mission, developed in partnership with JAXA, is specifically designed for this scenario. The spacecraft will be launched to the Sun-Earth L2 Lagrange point, the same gravitational balance point where JWST orbits, and will wait there, hibernating until a suitable target is discovered. That target could be a dynamically new solar system comet making its first approach from the Oort cloud, or, if we're extraordinarily lucky, an interstellar object. When a target is found and confirmed, Comet Interceptor will fire its engines and begin a transit toward an intercept trajectory. The mission consists of 3 separate spacecraft, a main probe and 2 smaller subprobes, which will separate before the encounter and fly through the coma at different distances, building a 3-dimensional picture of the gas, dust, and plasma environment around the nucleus. The instruments include mass spectrometers for analyzing the composition of dust and gas, cameras for imaging the nucleus and coma, magnetometers for measuring the comet's interaction with the solar wind, and a dust counter for measuring particle sizes and fluxes. This is the kind of science you can only do up close. The kind of science that turns a spectrum from JWST into a complete chemical inventory. Comet Interceptor is currently scheduled for launch no earlier than 2029, riding as a companion payload on ESA's aerial exoplanet mission. Once at L2, it could wait for years, even a decade, for the right target. The key is that the target doesn't need to be known in advance. The spacecraft is designed for opportunity. It sits and waits, like a spider in a web, until something interesting flies by. If an interstellar object is detected by Rubin early enough and on a trajectory that's geometrically favorable, Comet Interceptor could be redirected to intercept it. The flyby would last only hours. These objects move fast, but the data collected in that brief window would be revolutionary. Direct measurements of isotope ratios, in situ analysis of organic compounds, resolved images of an interstellar nucleus, particle-by-particle analysis of alien dust. For the first time in history, we would touch another star's material. Not metaphorically, physically. Atoms from another planetary system would pass through our instruments, be ionized in our mass spectrometers, and have their masses measured to parts per million. That moment hasn't arrived yet, but the architecture is being built. Rubin provides the eyes, Comet Interceptor provides the hands, and the interstellar medium provides the raw material, a continuous, if sparse, rain of fragments from planetary systems scattered across the galaxy and across cosmic time. Before we close, I want to mention one more compound detected in 3I/Atlas that connects it to the question of life's building blocks: hydrogen cyanide. HCN, 1 hydrogen atom, 1 carbon atom, 1 nitrogen atom, triple bonded in a simple linear molecule, is one of the most important prebiotic molecules in chemistry. Despite being toxic in its pure form, it's the gas used in execution chambers and the compound that gives almonds their distinctive smell. Hydrogen cyanide is a critical precursor for the synthesis of amino acids, nucleobases, and other biological molecules. The James Clerk Maxwell Telescope on Mauna Kea, a 15-meter submillimeter wave dish operating at wavelengths between 0.4 and 1 millimeter, detected HCN emission from 3I/Atlas on September 7, 2025. At that point, the comet was 2.33 astronomical units from the Sun. The measured HCN production rate was about 1.5 times 10 to the 25th molecules per second, which corresponds to roughly a kilogram of hydrogen cyanide being released into space every second. A week later, on September 14th, the production rate had tripled, climbing to 4.5 times 10 to the 25th molecules per second, or about 2 kilograms per second. The comet's HCN output was increasing as it approached the Sun, consistent with sublimation from progressively warming surface layers. The detection of HCN in an interstellar object is significant for astrobiology because it demonstrates that nitrogen-bearing prebiotic molecules are present in comets from other star systems. Combined with the organic compounds detected by SphereX in the 3 to 4 micrometer band, and the carbonyl sulfide measured by JWST, the picture that emerges is of a chemically rich object carrying a diverse inventory of molecules relevant to prebiotic chemistry. Cyanide is not exotic in solar system comets. It's one of the standard molecules detected in cometary COME, and its emission band near 388 nanometers is one of the classic optical signatures of cometary activity. What's notable about 3I/Atlas is that its HCN to water ratio appears consistent with solar system comets, even though its CO2 to water ratio is wildly anomalous. This suggests that some aspects of cometary chemistry may be universal across different star systems and different epochs, while others are highly dependent on local conditions. The nitrogen story doesn't end with HCN. The XRISM X-ray observations detected nitrogen ions in the charge exchange spectrum, confirming that nitrogen-bearing compounds are present in significant quantities in the coma. And the JWST MIRI observations detected a forbidden transition of atomic nickel, a separate nitrogen-bearing species, that provides additional constraints on the gas phase chemistry of the inner coma. The chemical inventory of 3I/Atlas, as assembled from the combined JWST, SphereX, VLT, Keck, JCMT, SWIFT, XRISM, and ground-based datasets, now includes water, H2O, carbon dioxide, CO2, carbon monoxide, CO, methane, CH4, carbonyl sulfide, OCS, hydrogen cyanide, HCN, cyanide radicals, CN, diatomic carbon, C2, hydroxyl, OH, atomic nickel, Ni, deuterated water, HDO, deuterated methane, CH3D, heavy carbon dioxide, superscript 1 superscript 3 CO2, heavy carbon monoxide, superscript 1 superscript 3 CO, water ice, organic compounds in the 3 to 4 micrometer band, and silicate-bearing refractory dust. That's a staggering list. More molecular species than have been detected in any previous interstellar object. More chemical detail than we have for most solar system comets. And the data analysis is still ongoing. New detections may yet emerge from the mountain of observations collected over the second half of 2025. Each molecule on that list is a clue, a piece of the puzzle of where 3I/Atlas came from, how it formed, what happened to it during its 10 billion-year journey, and what it can tell us about the chemistry of the galaxy at large. The puzzle isn't solved. It may never be fully solved, but the pieces are magnificent. Let me circle back to the deuterium, because I promised you fuel the universe forbids, and I want to make sure you understand the full depth of that phrase. To do that, I need to take you back to the very beginning. Not the beginning of 3I/Atlas, the beginning of everything. 13.8 billion years ago, the universe was born. In the first fraction of a second, the fundamental forces separated. In the first second, quarks condensed into protons and neutrons. In the first 3 minutes, a window so brief that your morning coffee takes longer, the temperature and density of the expanding universe were just right for nuclear fusion to occur. Not in a star, not in a reactor, in the universe itself. This is Big Bang nucleosynthesis, and it produced exactly 3 things in significant quantities: hydrogen, helium-4, and a small amount of deuterium, plus trace amounts of helium-3 and lithium-7. That's it. Every other element in the periodic table, carbon, oxygen, nitrogen, iron, gold, uranium, would have to wait for stars to forge them billions of years later. The amount of deuterium produced was specific and calculable. It depends on the baryon-to-photon ratio, essentially the density of ordinary matter in the early universe. The higher the density, the more efficiently deuterium is converted into helium, and the less deuterium survives. The lower the density, the more deuterium remains. The primordial D/H ratio, the fraction of hydrogen atoms that came out of the Big Bang as deuterium, is about 2.5 times 10 to the minus 5. That means roughly 1 in 40,000 hydrogen atoms emerged from the first 3 minutes as deuterium rather than ordinary hydrogen. This ratio is cosmologically important. It's one of the key tests of Big Bang cosmology. If you can measure the primordial deuterium abundance in pristine gas clouds at high redshift gas that has never been processed through a star, and compare it to the theoretical prediction based on the known baryon density, you get a beautiful agreement. The Big Bang model works. The nuclear physics is correct. The universe made exactly as much deuterium as the theory predicts. But here's the catch. Deuterium is fragile. It burns easily. The binding energy of a deuterium nucleus, a proton bound to a neutron, is only 2.2 million electron volts. That's tiny by nuclear standards. Stars destroy deuterium almost immediately upon ignition, fusing it into helium-3 at temperatures that are low by stellar core standards, only about 1 million Kelvin, compared to the 15 million Kelvin needed for sustained proton-proton fusion. As a result, every star that has ever lived has contributed to the destruction of the galaxy's deuterium budget. The gas in the Milky Way has been cycled through stellar interiors multiple times over 13 billion years. Each cycle burns some deuterium and doesn't replace it. Stars can't make deuterium. Only the Big Bang could make it. Every atom of deuterium in existence today is a survivor, a remnant of the first 3 minutes that managed to avoid being consumed by a star. In the local interstellar medium, the gas between the stars in our neighborhood, the D/H ratio has dropped from the primordial value of about 2.5 times 10 to the minus 5 to about 1.5 times 10 to the minus 5. Roughly 40% of the Milky Way's original deuterium endowment has been destroyed, gone forever, fused into helium in the cores of billions of stars over billions of years. This is the cosmic context for what we found in 3I/Atlas. The deuterium in its water ice at a D/H ratio of 0.95% isn't a measurement of the bulk galactic abundance. It's the product of molecular fractionation, a process that concentrates deuterium into specific molecules at extremely low temperatures. But the raw material, the deuterium atoms themselves, came from the Big Bang. They're among the oldest atoms in the comet. They were made in the first 3 minutes. Everything else, the carbon, the oxygen, the nickel, the silicon, was manufactured later by stars. But the deuterium is primordial, predates every star, every planet, every galaxy. When you look at 3I/Atlas's deuterium-rich ices, you're looking at Big Bang hydrogen that was concentrated by cold chemistry in the early Milky Way and then preserved for 10 billion years in the deep freeze of interstellar space. That's a chain of custody that stretches from the birth of the universe to the eyepiece of a telescope in 2025. Now let me connect this to the thing happening right now on Earth. Because deuterium isn't just an abstract cosmological curiosity. It's the linchpin of the most important energy technology our species is trying to develop. Nuclear fusion, the process that powers the sun. The process we've been trying to replicate in a controlled, sustained way since the hydrogen bomb demonstrated the uncontrolled version in 1952. The specific reaction that most fusion reactor designs aim to achieve is DT fusion. Deuterium plus tritium yields helium-4 plus a neutron plus 17.6 MeV of energy. This is the lowest temperature fusion reaction accessible to us. It ignites at about 100 million degrees, which sounds insane but is actually quite modest compared to the billion-plus degrees needed for other fusion fuels. ITER, the International Thermonuclear Experimental Reactor, currently under construction in Cataract, France, is designed to demonstrate sustained DT fusion at reactor scale for the first time. It's the most expensive science experiment in human history, with a budget exceeding $22 billion. When it achieves full power, it will produce 500 megawatts of thermal energy from just 50 megawatts of input, a tenfold energy gain. The first sustained fusion burn is targeted for the early 2030s. Private companies like Commonwealth Fusion Systems, TE Technologies and Helion Energy are pursuing alternative designs. Compact tokamaks with high-temperature superconducting magnets, field-reversed configurations, pulsed fusion approaches, racing to achieve commercial fusion power within the next decade. Every one of these projects, government and private, magnetic and inertial, needs deuterium. It's the universal fusion fuel. And on Earth, deuterium is relatively easy to obtain. Seawater contains about 1 deuterium atom for every 6,500 regular hydrogen atoms, AD/H ratio of about 0.015%. We can extract it through electrolysis and distillation. The world's oceans contain enough deuterium to power human civilization at current energy consumption levels for hundreds of millions of years. But here's the twist that makes 3I/Atlas so poetically resonant. The deuterium concentration in 3I/Atlas's water ice is about 60 times higher than in Earth's oceans. 60 times. If you could somehow mine this comet's ice, you'd have a fantastically enriched source of fusion fuel compared to terrestrial seawater. Nobody is proposing to mine interstellar comets for deuterium. That would be absurd. The comet is 270 million kilometers away and moving at 58 kilometers per second in the wrong direction. But the fact that the universe can produce such concentrated deuterium, through nothing more than cold chemistry and patient time, is remarkable. It tells us that deuterium-rich ices are a natural feature of the cosmos, not a peculiarity of our local environment. Wherever ancient, cold molecular clouds exist or once existed, similar fractionation could have occurred. And if we ever do explore the outer reaches of other star systems, the Oort clouds and Kuiper belts of alien suns, we may find ice deposits with deuterium concentrations that make Earth's oceans look dilute, the raw material for fusion power, scattered across the galaxy in frozen comets, waiting to be harvested. That's a long way off. But it starts with understanding the chemistry, and 3I/Atlas just gave us a masterclass. Avi Loeb, predictably, has something to say about this. In a blog post from late March 2026, Loeb pointed out that deuterium, when combined with tritium, is the fuel of choice for controlled nuclear fusion. And he asked a provocative question: could the extraordinary deuterium enrichment of 3I/Atlas be a technosignature? A sign that some intelligence, somewhere in the ancient Milky Way, manufactured deuterium-rich material fusion fuel and stored it in the form of a comet-like body? It's a thought experiment worth having, because Loeb is right about one thing: we should not assume natural explanations without testing them against the data. That's good science. The history of astronomy is full of examples where natural explanations turned out to be correct, but only because they were rigorously tested against exotic alternatives. Pulsars were initially dubbed LGM, Little Green Men, by Jocelyn Bell Burnell's supervisor, because the regularity of their radio pulses seemed too precise to be natural. They turned out to be rapidly spinning neutron stars. Natural but astonishing. Gamma-ray bursts were initially mysterious enough to inspire speculation about alien warfare. They turned out to be the deaths of massive stars and the mergers of neutron stars. Natural but violent beyond comprehension. In the case of 3I/Atlas, the deuterium enrichment is well explained by known astrochemical processes. Grain surface fractionation at temperatures below 30 Kelvin, in a dense molecular cloud core, over timescales consistent with the comet's estimated formation epoch. The numbers work. The physics is well established. Laboratory experiments reproduce the relevant reactions. Occam's razor slices cleanly here. The simplest explanation consistent with the data is that 3I/Atlas formed naturally in an environment where cold chemistry produced extreme deuterium enrichment. No technology required. But Loeb's question isn't silly. It's the kind of question we should be asking. And the breakthrough LISTEN observations, which found no artificial signals, are the kind of evidence that should be gathered in response. Science proceeds by proposing hypotheses and testing them against data. The natural origin hypothesis for 3I/Atlas is strongly supported. The artificial origin hypothesis is not supported by any current evidence. But the very fact that we can conduct these tests, that we have the telescopes, the instruments, the mathematical frameworks, is a testament to the extraordinary capability of modern astronomical science. And the next interstellar visitor might be different. But before we look to the future, let's reckon with what 3I/Atlas tells us about the past. Not just the past of one comet, but the past of our entire galaxy. Consider the implications. 3I/Atlas formed 10 to 12 billion years ago in a protoplanetary disk around an ancient metal-poor star. That means planetary formation, the assembly of rocky and icy bodies from a disk of gas and dust, was already happening when the Milky Way was less than 3 billion years old. The galaxy was young. The heavy elements produced by supernovae were just beginning to accumulate. And yet, already there were disks. Already there were comets. Already there was ice chemistry complex enough to produce water, carbon dioxide, carbon monoxide, methane, carbonyl sulfide, and organic compounds. We know from astronomical surveys of other galaxies that the period from roughly 8 to 12 billion years ago, cosmic noon, was the era of peak star formation. Across the observable universe, galaxies were churning out stars at rates 10 to 20 times higher than today. The Milky Way was no exception. The thick disk population, the dynamically hot, metal-poor stellar population to which 3I/Atlas likely belongs, was being built during this epoch. And where there are stars, there are disks. Where there are disks, there are planets. Where there are planets, there are leftover fragments, asteroids and comets, that get ejected into interstellar space by gravitational encounters. 3I/Atlas is one such fragment. But it's not just any fragment. It's a fragment that carried within it a chemical record of conditions in an early universe protoplanetary disk. The deuterium enrichment tells us the temperature. The carbon isotopes tell us the metallicity. The CO2 dominance tells us the comet's position within the disk, far from the parent star, beyond the CO2 ice line. The methane tells us about the deep interior, preserved for 10 billion years beneath a shield of cosmic ray processed ice. No telescope can observe a protoplanetary disk from 10 billion years ago. Those disks are gone. The stars they orbited have evolved, some into white dwarfs, some into neutron stars, some still burning feebly as ancient red dwarfs. We cannot go back in time to study early planet formation directly, but 3I/Atlas brought a sample to us. A piece of that ancient disk, delivered across 10 billion years of galactic history, right to our solar system. We didn't have to build a time machine. The universe sent one. This raises a question that sits at the intersection of astrobiology and philosophy. Could objects like 3I/Atlas carry the building blocks of life between star systems? This idea, Panspermia, literally seeds everywhere, is old. It dates back to the ancient Greeks, was revived by Lord Kelvin and Svante Arrhenius in the 19th century, and has been debated by astrobiologists ever since. The basic concept is straightforward. Life requires organic chemistry. Comets are loaded with organic compounds, amino acids, nucleobases, sugars, and their precursors have all been detected in meteorites and cometary samples. If a comet from one planetary system is ejected into interstellar space and eventually captured or impacts another system, it could, in principle, deliver organic material to a young planet. 3I/Atlas shows that this delivery mechanism is plausible on galactic scales and timescales. It demonstrates that icy, organic-rich bodies can survive for billions of years in the interstellar medium, maintaining their volatile inventory, at least in their interiors, despite relentless cosmic ray bombardment. The cosmic ray process crust actually helps. It acts as a radiation shield and thermal insulator, protecting the deeper layers. Now, could life itself survive such a journey? That's much less certain. The cosmic ray dose to the outer layers of an interstellar comet over 10 billion years is lethal to any known organism many times over. Even extremophiles, radiation-resistant bacteria like Deinococcus radiodurans, would be destroyed within a few million years at the radiation levels in the interstellar medium. The process zone extends 15 to 20 meters deep, and any biology in that zone would be thoroughly sterilized. But organic molecules are tougher than organisms. Amino acids, for example, are simple and robust. They can be synthesized by cosmic ray irradiation of simple ices. In fact, that's probably how some of them formed on 3I/Atlas in the first place. So while 3I/Atlas is unlikely to carry living organisms from an ancient star system, it could easily carry the chemical precursors of life. The building blocks, the letters of the genetic alphabet, scattered across the galaxy by the ejection of comets from every planetary system that has ever existed. The Spherex December observations detected organic emission features in the 3 to 4 micrometer band, wavelengths characteristic of carbon-hydrogen stretching vibrations in complex organic molecules. These organics were streaming off 3I/Atlas as part of its post-perihelion eruption. We don't yet know the specific molecules involved. That will require higher resolution spectroscopy than Spherex can provide. But their presence is consistent with a comet rich in prebiotic chemistry. If interstellar comets have been delivering organic material to young planetary systems for the entire history of the Milky Way, then the chemistry of life may not have had to start from scratch on each habitable world. Each planet that formed in a system with its own comet population would also receive a steady rain of interstellar cometary material, fragments from other systems, other eras, other chemical environments. The organic inventory available to a young planet would be a blend of local and interstellar contributions. This doesn't solve the origin of life. We still don't know how self-replicating molecules first assembled from simpler precursors. But it does suggest that the raw materials were more widely available and more diverse than we might have assumed based on studying our solar system alone. There's another implication of 3I/Atlas that speaks directly to the search for life on exoplanets. And it has to do with what the comet tells us about the chemistry of other star systems. For the past 2 decades, the study of exoplanets has focused on detection, finding planets, measuring their sizes and masses, determining their orbital periods. The next frontier is characterization, determining what these planets are made of, what their atmospheres contain, whether they have the ingredients for habitability. JWST is at the forefront of this effort, measuring the atmospheric compositions of transiting exoplanets by observing starlight filtered through their upper atmospheres. The technique, transmission spectroscopy, has already detected water vapor, carbon dioxide, and other molecules in the atmospheres of hot Jupiters and subneptunes. But there's a gap. We can study the atmospheres of large, close-in exoplanets with current technology. We cannot yet characterize the surfaces or bulk compositions of small, rocky, Earth-like worlds in the habitable zones of their stars. The signal is too faint. The planet is too small relative to its star. Interstellar objects like 3I/Atlas offer an alternative window. They provide direct samples, real physical specimens, of material from other planetary systems, not filtered through a distant atmosphere, not inferred from a transit dip. Actual ice and dust and organic molecules, measured at close range, isotope by isotope, molecule by molecule. The JWST data on 3I/Atlas tell us that at least one ancient planetary system had a chemistry dominated by CO2 over water in its outer disk, with extreme deuterium enrichment indicating formation temperatures below 30 Kelvin. That's a specific quantitative constraint on the physical conditions in an exoplanetary system, a constraint we couldn't get any other way. If we can build up a library of such measurements from 3I/Atlas, from the next interstellar visitor, from the dozens that Rubin Observatory is expected to find over the coming decade, we'll have an empirical database of exoplanetary chemistry. Not models, not predictions, actual measurements of what other star systems are made of. That database, cross-referenced with what we learn from exoplanet atmospheres and protoplanetary disk observations, will revolutionize our understanding of how planets form, how common habitable chemistry is, and whether the conditions that led to life on Earth are typical or exceptional. 3I/Atlas is the first entry in that database, and it already rewrote the textbook. One more observation deserves mention before we close. It's about X-rays, and it's about how the universe itself lit up 3I/Atlas from the inside out. In late November 2025, JAXA's XRISM X-ray Observatory, launched in September 2023 as a replacement for the ill-fated Hitomi satellite, detected faint X-ray emission from 3I/Atlas. The observation, using the STEND imaging spectrometer over a 17-hour integration, revealed a diffuse glow extending roughly 400,000 kilometers around the nucleus. This was the first X-ray detection of any interstellar object. The first time we've seen an interstellar comet glow in the highest energy light the electromagnetic spectrum offers. X-rays from comets aren't powered by the comet itself. The comet isn't radioactive. It isn't hot enough to emit X-rays thermally. Instead, the X-rays are produced by a process called solar wind charge exchange. Here's how it works. The solar wind, a stream of highly ionized atoms, mostly hydrogen and helium, flowing outward from the sun at several hundred kilometers per second, crashes into the comet's gas coma. The solar wind ions are missing some of their electrons. They're hungry for electrons. When they encounter neutral gas molecules in the coma, water, carbon dioxide, carbon monoxide, they steal electrons from those molecules in a process called charge exchange. The captured electrons arrive in highly excited energy states and cascade down to lower states, emitting X-ray photons in the process. The XRISM spectrum of 3I/Atlas showed excess emission from carbon, nitrogen, and oxygen ions, exactly the species you'd expect from charge exchange between the solar wind and the molecular gases identified by JWST. The X-ray luminosity was faint. These were long, careful observations pushing the telescope to its limits, but the detection was secure. Why does this matter? Because X-ray observations provide a unique probe of the comet-solar-wind interaction. They tell us about the total gas production rate. The more gas in the coma, the more charge exchange, the brighter the X-rays. They tell us about the composition of the solar wind at the comet's location. And they tell us about the spatial distribution of neutral gas, which can reveal structures like jets, shells, and asymmetries that might not be visible in optical or infrared images. For 3I/Atlas, the X-ray detection confirmed that the comet's gas coma was substantial, extending hundreds of thousands of kilometers in all directions. Even at a distance of 2 astronomical units from the Sun, the comet was pumping out enough gas to create a significant interaction region with the solar wind. This is consistent with the high total mass loss rates measured by JWST and the sustained activity observed post-perihelion. ESA's XMM Newton X-ray telescope also observed 3I/Atlas around the same time, providing complementary data at different X-ray energies. The combined XRISM and XMM Newton dataset will allow detailed modeling of the charge exchange process and may reveal whether the gas composition changes with distance from the nucleus, a test of the extended source model for water production. We live in a galaxy that almost certainly teems with interstellar objects. Models suggest that the Milky Way contains on the order of 10 to the 26 such objects. That's 100 trillion ice and rock fragments drifting between the stars, each one a potential message in a bottle from another planetary system. Some of those objects are as old as 3I/Atlas or older. Some are young, freshly ejected from active planetary systems. Some carry chemistry similar to our solar system's comets. Some carry chemistry utterly unlike anything we've seen. The ones we find will depend on our instruments, their sensitivity, their sky coverage, their speed of response. The Rubin Observatory will be a game-changer. JWST and its eventual successor will provide the spectroscopic muscle to read whatever chemical stories these visitors carry. And perhaps, if we're ambitious, if we invest, if we dream big enough, we'll intercept one. We'll fly a spacecraft through its coma, or alongside its nucleus, and measure its composition with an accuracy that no Earth-based telescope can match. Until then, we work with what we've got. And what we've got right now is the dataset from 3I/Atlas. A dataset that tells us the young Milky Way was building planets and comets in conditions radically different from today. That carbon dioxide can dominate cometary chemistry in ways we'd never predicted. That methane can survive billions of years of cosmic ray bombardment if it's buried deep enough. That deuterium fractionation in ancient molecular clouds can reach levels that rewrite the boundaries of astrochemistry. That the universe in its youth was a different place, colder place, a place where the raw material of fusion, heavy hydrogen, could be concentrated into ice at levels the modern galaxy has forgotten. 3I/Atlas is gone now. We're going, receding at 58 kilometers per second. Each second, it puts another 36 miles between itself and the sun. By the time you finish listening to this, it will be thousands of miles farther away than when you started. It will cross the orbit of Jupiter. It will sail past the orbit of Saturn. It will drift through the Kuiper Belt, if you can call it drifting at 130,000 miles per hour. It will pass beyond the heliopause, where the solar wind gives way to the interstellar medium. And then it will rejoin the great dark ocean it sailed for 10 billion years before it stumbled into our gravity well. It won't think about us. It's a rock, a beautiful, ancient, chemically complex, scientifically staggering rock. But a rock nonetheless. We, however, will think about it for a long time. The data is in our computers. The spectra are in our archives. The papers will multiply. The models will be refined. And someday, years from now, decades from now, some graduate student will pull up the 3I/Atlas dataset and find something in it that nobody noticed in 2025. Some signal, some pattern, some molecular fingerprint that becomes interpretable only in light of future discoveries. That's how science works. The data outlives the comet. The questions outlive the answers. And sometimes, the significance of a discovery only becomes clear when it's placed in the context of things we haven't learned yet. Think about the Rosetta Stone. When it was found by Napoleon's soldiers in Egypt in 1799, nobody could read Egyptian hieroglyphics. The stone was a curiosity, a slab of granite with 3 scripts on it. It took 23 years before Jean-François Champollion decoded the hieroglyphics using the Greek text as a key. The stone didn't change. What changed was our ability to read it. 3I/Atlas is our Rosetta Stone from the stars. We can read parts of it now: the CO2 dominance, the deuterium enrichment, the methane emergence, the cosmic ray processing, the carbon isotope age. But there are lines in the spectrum we don't yet understand. Molecular features we can't yet identify. Ratios we can't yet interpret in the context of exoplanetary disk models that haven't been developed. The data will wait. It's patient. It's digital. It will sit in the Mikulski archive for space telescopes and in observatory databases around the world, ready for the next generation of scientists to extract meaning from it with tools we haven't invented yet. Let me leave you with one final thought, one final image to carry with you into sleep, or into your commute, or into whatever comes next in your day. Right now, at this very moment, there are objects drifting through the space between the stars that are older than our sun, older than our galaxy's spiral arms, older than many of the stars you can see with your naked eye on a clear night. These objects carry, frozen in their ices, the chemical memory of conditions that existed when the universe was young, when star formation was at its peak, when the building blocks of planets were being assembled in protoplanetary disks around the first generations of metal-poor stars. Some of these objects are the size of mountains. Some are the size of houses. Some are the size of grains of sand. They drift at speeds of tens of kilometers per second, following orbits around the Milky Way that take hundreds of millions of years to complete. They pass close to stars, are gently deflected, and continue on their way. They are bombarded by cosmic rays, their surfaces slowly transformed by radiation chemistry. But their interiors remain sealed, pristine, unchanged since the day they were ejected from their parent systems. Once in a great while, by pure chance, one of these objects passes close enough to a star that it becomes visible. Its ices begin to sublimate. Coma forms. Tail develops. And if that star happens to be our sun, and if our telescopes happen to be looking in the right direction at the right time, we see it. We get a few months, maybe a year if we're lucky, a brief window in which to aim every instrument we have at this visitor from another time and another place, to read its chemical fingerprint, to measure its isotopes, to learn what it can teach us about the universe beyond our solar system. And then it's gone, back into the dark, back into the silence between the stars, carrying its secrets, most of them still unrevealed, back into the void. 3I/Atlas was one such visitor, the third we've ever found, probably not the last, almost certainly not the most extraordinary. But it was the first to show us, in quantitative spectroscopic isotopic detail, just how different the chemistry of other star systems can be from our own. The first to carry deuterium at concentrations 10 times beyond our experience. The first to reveal methane emerging from beneath a cosmic ray process crust. The first interstellar object observed in X-rays. The first photographed from the surface of Mars. It was a once-in-a-generation event that happened to occur during a generation when our telescopes were powerful enough, our spacecraft were numerous enough, and our scientific community was coordinated enough to capture its fleeting passage in extraordinary detail. We were ready, barely, but we were ready, and the next time, we'll be readier. And somewhere, out there in the dark, another visitor is approaching. We can't see it yet. It's too faint, too distant. Perhaps it's still beyond the orbit of Neptune. a dim point of light crawling through the outer solar system at a speed that, while staggering by terrestrial standards, looks like glacial drift against the background stars. Perhaps it hasn't even entered the sun's gravitational domain yet. Perhaps it's still in true interstellar space, still drifting in the black, still cold, still sealed. But it's coming, drawn by the gravity of a star, our star, on a hyperbolic path from some other corner of the galaxy, some other era of cosmic history. It might be carrying water ice from a young, metal-rich system where planets are forming right now, or sulfur compounds from a disk around a red dwarf where no complex life could ever take hold, or amino acids from a cloud that collapsed 5 billion years ago and seeded a system with organic chemistry before the first microbe ever stirred, or something we've never seen before, something we don't have a name for, something that will make 3i/Atlas look ordinary by comparison. It's out there. The galaxy is full of these wanderers. And next time, with Rubin's eyes and Comet Interceptor's hands and JWST's spectral vision and a global community of astronomers poised to respond, we'll find it sooner. We'll study it longer. We'll learn more. And maybe, just maybe, we won't only watch. Maybe we'll go meet it. This has been CosmHush. Thank you for listening. The universe is vast and cold and very, very old, but it still has stories to tell. Stories written in isotopes and ices and the faint glow of ancient molecules sublimating for the first time in 10 billion years. Stories that cross the boundaries between star systems and epochs, delivered to our doorstep by the random walk of gravity. You just have to know where to look. And sometimes you don't have to look at all. Sometimes the universe comes to you